Hello, and welcome back to the course on Physics for Engineers. So this is now the last chapter of this course, which will be all about optics. So this is chapter 15, optics. So before we proceed with the first lesson for this course, let us first review some concepts. So in the previous lessons, we have discussed about electricity and magnetism and their relationship called electromagnetism. So in the last part of electromagnetism, we have described different examples of electromagnetic interaction where one is called light, which is just a combination of two concepts, electromagnetism and waves. So light is an electromagnetic wave. So for the first lesson, for chapter 15, let us first explore what is the nature of light. Is it a particle? Is it a wave? Or is it both? So we'll try to explore that in this lesson. So light, uh, let's first discuss how light, the concept of light was created. So Isaac Newton theorized that light is a stream of particles, and he actually termed those particles as corpuscles. Now, in 1665, evidences due to experiments done by scientists, evidence of wave properties of light began. So Isaac Newton theorized that it's a particle, but in 1665, evidences emerged that light is also a wave. In 1887, Hertz showed that light is an electromagnetic wave. So it now adds further to the nature of light that it is indeed a wave. Now, absorption and emission of light experiments revealed that light is also a particle. So the energy carried of this particle is in discrete bundles, and this bundle or this quanta is what we call photon. So basically, you can describe light as a particle in terms of photons, one bundle of energy. And that's basically, you can tell that that's one particle of light, a photon. So light is actually dual. It's both a particle and a wave. And we call this property, this nature of light as the wave-particle duality of light. So the wave-particle duality of light reconcile the wave and the particle theories of light. And this is discussed specifically in this higher physics subject or high advanced physics subject called quantum electrodynamics. So the wave model of light can be used if you're just studying light propagation or optics, especially geometric optics. And the particle model of light can be used when you are dealing with absorption and emission of light. So you can use both either of the models depending on the situation, depending on whether you're just studying how light behaves, how light propagates through a material, then you use the wave model. But if you are trying to discuss about the absorption and emission of light, then you use the particle model. So light, the study of light is basically optics. It's a branch of physics which studies the behavior and the propagation of light. So before we uh, study optics, which is the last chapter of this course, let's first take a look at the spectrum of light. So light is an electromagnetic wave. It's an electromagnetic radiation. And the light that we can see, the white light and the colors, are just a very tiny, very small part of this whole spectrum. So the visible region, the light that we can see, that can be seen by our eyes, is just a very tiny part of the whole light spectrum. So what we can see is from violet, That's 400 nanometer wavelength to 700 nanometer wavelength, which corresponds to red. That's the only region that's visible to our eyes. Beyond violet, that's now ultraviolet. And beyond ultraviolet, you have X-rays, and then beyond X-rays, you have gamma rays. So decreasing wavelength, it's actually increasing energy or frequency and energy. So ultraviolet light has much higher energy than visible light. So UV from the sun actually can can cause cancer because of the energy and how much more X-rays and how much more gamma rays. So if you're exposed to gamma radiation, you will surely die, unless of course you're the Incredible Hulk. Okay, so beyond red, you have infrared. Again, UV, X-rays, gamma rays, these are now outside the visible region of light. We can no longer see this light. Similar with above the red light. So infrared, we cannot see infrared, but we can feel it as heat. So infrared is also in our remote controls that uses infrared. Microwave, it's much higher than, much lower energy. So decreasing energy, increasing energy towards gamma rays. This is actually decreasing energy in the opposite direction. So basically, infrared, microwave, and radio waves. Radio waves, that includes Bluetooth, Wi-Fi, AM, FM. Those are radio waves, and they're actually very low energy, low frequency, and low energy electromagnetic waves or light. And we cannot see this light. We cannot see an AM radio wave, an FM radio wave. We cannot see Bluetooth. We cannot see Wi-Fi, because those are now beyond our visible uh, capacity of our eyes. Now, even though these are lower energy wavelength, there's a certain region here, the microwave region, which is harmful to us, because uh, microwave, or rather water, is very sensitive to microwave. When you microwave water, water will start to boil, water molecules will start to get energetic. The water actually absorbs microwave. So microwave is lethal, or it's harmful to anything that contains water. So if you just want to heat your food in the oven, you can use microwave oven to heat it. But if you place a being, a live being there, or a human being, that you will surely die, because our bodies are made of 75% water. So there's just a specific frequency for microwave that our bodies or water will react to. So microwave is harmful to anything that contains or it makes water boil. Microwave makes water boil. So since we are made of water, our water in our body will boil, and that we will die if we were exposed to a higher dose of microwave. Okay. So there are many ways to represent light. We can represent light as a wave front. So a wave front describes the wave propagation of light. So physical optics, it can represent the wave's crest or the wave drops. So similar to sound, sound is a wave, light is also a wave. So the wave fronts are the crest and troughs of the waves are actually spherical, or the wave fronts are actually spherical in nature. So we can also represent light as a ray. So an imaginary line along the direction of travel of the wave. So in this case, this is the ray. An imaginary line along the direction of the travel of the wave. So that's basically geometric optics. So the relationship between wave fronts and rays is, if these curves here, the spherical curves here are the wave fronts, then these lines here, which is always perpendicular to the wave fronts, are the rays. So the rays are always perpendicular to the wave fronts. And instead of representing light as wave fronts, it's actually more convenient to represent light in terms of rays, because you're just looking at the direction of the propagation. So if this is your electromagnetic wave, these are your wave fronts, and the ray will be perpendicular to that wave front. So always wave fronts and rays are perpendicular to each other. So from this moment on, we will just represent light using rays. But that means that if we have a ray in this direction, that means that there will be a wavefront perpendicular to that ray. Okay, so let's now discuss the different sources of light. So the basic source of light is electric charges in accelerated motions, or basically electric charges that are accelerating. When you say accelerating, it's either speeding up or slowing down. It must not be moving at constant velocity. So one example of that is an oscillating or accelerating charge in general. So if you have a charge that is oscillating, say oscillating up and down, take note that a charge has an electromagnetic field. Now, if it moves up and down, what will happen to its electromagnetic field lines? It will also wave. And that basically creates an electromagnetic wave or light. So it's basically just the electric and magnetic field lines that are waving. So if the electric field and the magnetic field lines are waving, you generate an electromagnetic wave or light. So basically, uh, the electric field, this is the electric field, the purple one, and this is the magnetic field, the green one. So they are waving basically, and they are waving in this direction, and the wave is traveling in this direction. So basically, this picture here will generate light that is moving in this direction, and this direction is the direction of the ray. Okay? So this, you can think of this line as the ray, the direction propagation of light. So that's the basic source of light, a charge that is oscillating or accelerating, speeding up or slowing down, causing the electromagnetic field lines to wave. So in general, all bodies actually emit electromagnetic radiation because we are composed of atoms, and inside atoms are electrons, and electrons are always moving, accelerating inside an atom. So basically, we are generating light. All bodies emit light. So in our case, we are actually emitting infrared, and we can see infrared if you have a thermal scanner. Just like in airport, there are thermal scanners to scan your body temperature. So you sometimes you discontinue to emit light only when you're dead. Actually, if you're dead, you still emit some form of infrared light. But all bodies uh, emits infrared radiation or infrared light. But again, it's invisible to us. You need a specific device such as a thermal scanner to view that. So this is an example of basically when you hit something, it actually emits infrared. So for example, the gas stove. If you hit your gas stove, that will actually emit infrared. But you cannot see it, but you can feel it as heat. So such as the sun emits infrared radiation, but we cannot see it, we can feel it though as heat. So heat is basically an indicator of thermal radiation. Now, in certain instances, if the temperature of your stove is high enough, it will emit visible light, and it will start with red, then orange, yellow, green, blue, violet. If the color is violet, then that's already very hot. And if the color is white, meaning all of the colors, white is just a combination of all colors. If you see a white light, a white hot object, that's the hottest of all the visible colors. So don't touch a white hot plate. Okay. So other sources of light include electric discharges through ionized gases. So basically, this is ionized gases plasma. So example of these are mercury lamps, fluorescent lamps, stars such as our sun, or in general, plasma. So usually in our old fluorescent lamps, you use some kind of gas there inside, and then when electricity flows through that gas, it ionizes that gas, and when a gas is ionized, it will discharge. It will emit light. So that's one source of light. So of course, our sun or any star in particular or in general, so they actually emit the whole spectrum. Some of it are just filtered by our atmosphere. But UV can still pass through our atmosphere. Infrared can still pass through our atmosphere. Visible light can still pass through our atmosphere. So when we look at our sun, it will look yellowish. That's the visible, because that's the yellow is the most highest intensity that we can see. But it still emits. It still we we it still emits all of the colors, and in fact, it still emits infrared because we feel the heat of the sun, and that is infrared. And it also emits UV, but we don't feel UV. We just know that we are exposed to UV when your skin darkens, which leads to basically cancer. So skin cancer are caused by UV exposure from the sun. So the sun emits the whole spectrum of light: the UV, the visible, the infrared, and etc. And the other colors of the other spectrum of light. So the last source of light that we will discuss is laser. It's basically an acronym for light amplified through stimulated emission of radiation. So there are many applications of laser. So in a laser, the atoms of the material, whether you use a solid laser, solid state laser, liquid state laser, or a gas laser. So you can have three types of laser: solid state, liquid state, or gas. So the atoms in these states or in these spaces are stimulated to emit light in a cooperative, coherent fashion. And it can produce a narrow beam of radiation that can be very intense and nearly monochromatic, just one single frequency or one color. So that's the advantage of lasers. So lasers has a lot of applications such as disco lights. So there are uh, medical, uh, educational, academic applications of lasers. Okay, another property of light is the speed. Its speed. So all electromagnetic radiation or all light that travels in vacuum or in space, in empty space, travel at this speed of light, 2.99, or we'll just round off this to 3. 3 times 10 to the 8 meters per second. So this is what we call the speed of light in vacuum. So this is a simulation of how fast how fast is 3 times 10 to the 8 meters per second. So light actually travels from Earth to the moon in just 1.255 seconds. So as we're talking right now, light is traveling from Earth to the moon in just 1.255 seconds. So that's actually very fast. This speed is actually very, very fast. So a light from the sun travels to Earth in 8 minutes. So that tells you how far the sun really is with respect to Earth. So in the instance that our sun, uh, say instantly disappeared, we will still notice that 8 minutes later, because light travels 8 minutes from the sun to the Earth. So based on this speed of light, this is a universal constant. We define 1 meter as the distance light travels in 1 over 300 millions of a second, or that is approximately 3.36 nanoseconds. So when light travels for 3.36 nanoseconds, the distance that it travels is 1 meter. That is the definition of 1 meter, with the 1 second defined by the Cesium clock. So 1 light year there are so many misconceptions about this. 1 light year is not time, it's not a year, it's a distance. So 1 light year is actually the distance that light travels in 1 year. And that is approximately 26.7 trillion kilometers. So that's a very far distance. So for example, the nearest star to us, Proxima Centauri, is around 4 to 5 light years away. So the speed of light is what we call the speed limit of our universe. So nothing can travel faster than light as of now. No, but that is the theory states that that is uh, the fastest speed in the universe. So it's the speed limit of our universe. So only light can travel the fastest. Okay, so that is the end of this lesson, the lesson on the nature of light. So in our next lessons, we will be discussing about how light behaves and how light propagates through a material. So I will see you again in the next lesson. Bye bye.